Place both palms flat on the nearest hard surface and press down firmly for 3 seconds. Feel the resistance. That solidity you feel is mostly empty space pushing back, because the atoms in that surface are almost entirely vacuum, electrons orbiting nuclei across distances proportionally as vast as planets orbiting a sun. And yet something fills that apparent emptiness with enough structure to hold your weight. That something is the subject of what follows. The question is not whether empty space is truly empty. Physics settled that decades ago. The question is what, precisely, is there? How do we know it is there? And why our best calculation of its energy is wrong by a factor so large it constitutes the most embarrassing number in the history of science. Start with the principle that makes all of this unavoidable. In 1927, Werner Heisenberg, working at the University of Copenhagen, established that certain pairs of physical quantities cannot both be precisely defined at the same time. Position and momentum form one such pair. The more tightly you confine a particle in space, the more wildly its momentum must fluctuate. This is not a limitation of instruments. It is not a matter of disturbing the particle when you measure it. It is a structural feature of quantum reality, baked into the mathematics of wave functions and confirmed in every precision experiment conducted since. But Heisenberg's constraint extends beyond particles to fields. A quantum field is a physical entity that assigns a value to every point in space, the way temperature assigns a value to every point in a room, except that the field value obeys quantum rules. The electromagnetic field is one such field. The electron field is another. The quark fields, the Higgs field, the neutrino field, each is a separate quantum entity spread across all of space simultaneously. And here is the constraint that cannot be escaped. A quantum field cannot be set to exactly zero everywhere. Setting it to zero would mean knowing its state with absolute precision, both its value and its rate of change, at every point. The uncertainty principle forbids this. The field must fluctuate. It must carry residual energy even when no particles are present, even when the temperature is absolute zero, even when every photon has been removed and every atom has been evacuated. This residual energy is called zero-point energy, the minimum energy a quantum system retains in its lowest possible state, the ground state. The mathematical form is exact. For a quantum harmonic oscillator, which is the mathematical model for a single mode of a quantum field behaving like a mass on a spring, the ground state energy is 1/2 multiplied by Planck's constant multiplied by the frequency of that mode. 1/2 h bar omega, not zero, never zero. The fraction 1/2 is not an approximation. It is the precise solution to the Schrödinger equation for the harmonic oscillator ground state, and it tells you that even a spring cooled to absolute zero retains kinetic energy that cannot be extracted, cannot be transferred, cannot be made to vanish. Now extend this to the vacuum of space. The vacuum is not one oscillator. It is an uncountable collection of oscillators, one for every field mode at every point in space across every possible frequency. Each electromagnetic mode, each matter field mode, each carries its own 1/2 h bar omega. The vacuum is the sum of all of these ground states simultaneously. The vacuum hums. It does not hum metaphorically. It carries real physical energy distributed across real physical fields, and this energy produces measurable forces on real objects in real laboratories. The cleanest demonstration was predicted in 1948 by the Dutch physicist Hendrik Casimir, working at Philips Research Laboratories in Eindhoven. Casimir considered two flat, uncharged, perfectly conducting metal plates placed in a vacuum a few micrometers apart. No charge, no current, no magnetic field, no thermal radiation. Classical electromagnetism predicts zero force between them. Casimir's quantum calculation predicted something different. Between the plates, the electromagnetic field modes are constrained. Only those modes whose wavelengths fit an integer number of half wavelengths into the gap are allowed. The same restriction that governs standing waves on a guitar string clamped at both ends. Outside the plates, no such constraint applies. Every wavelength is permitted. The result is an asymmetry. More field modes exist outside the gap than inside it. More zero-point energy exists outside than inside. This creates a net inward pressure, a force pushing the plates toward each other, generated by nothing more than the structure of the vacuum itself. Casimir calculated the magnitude. The force per unit area between two ideal conducting plates separated by a distance d is equal to pi squared times h bar times c divided by 240 times d to the fourth power. This force falls off as the fourth power of the separation, which makes it extraordinarily weak at any macroscopic distance, but measurable at micrometer scales. The experimental confirmation came in 1997, when Stephen Lamoureux, then at the University of Washington, measured the Casimir force with a precision of 5%, bringing the measured value into agreement with Casimir's 1948 prediction. 5% precision on a force generated by the quantum vacuum, not a theoretical abstraction, a laboratory measurement. The vacuum pushes. The vacuum pushes metal plates together with a calculable, measurable, reproducible force that no classical theory can explain. Lamoureux's 1997 measurement is not the only evidence. A second, independent line of proof comes from atomic spectroscopy. In 1947, Willis Lamb at Columbia University measured the energy levels of hydrogen with a precision that exposed a discrepancy. The electron in hydrogen's first excited state exists in two sublevels, labeled 2s1/2 and 2p1/2. The Dirac equation of relativistic quantum mechanics, which was the best available theory at the time, predicted these two levels should have identical energies. Lamb measured them and found they did not. The 2s1/2 level sat about 1058 MHz higher in energy than the 2p1/2 level. 1058 MHz. This is the Lamb shift, and it is caused by the interaction of the electron with vacuum fluctuations. The electron in your hydrogen atom does not orbit in silence. It is constantly being nudged by virtual photons arising from the zero-point fluctuations of the electromagnetic field. These nudges average to zero over time, but their mean square value does not vanish, and this residual jostling smears the electron's effective position slightly, changing the energy of levels that have different spatial distributions near the nucleus. The 2s1/2 and 2p1/2 levels respond differently to this smearing, which produces the measured 1058 MHz gap. Lamb won the Nobel Prize in Physics in 1955 for this measurement. The 1058 MHz Lamb shift is not an anomaly. It is a precision confirmation that the vacuum is active at atomic scales, interacting with electrons constantly. The vacuum is not a passive backdrop, it participates. It is worth being precise here about the language of virtual particles, because popular accounts often mislead. The phrase virtual particles refers to a calculational tool, a term in a perturbation expansion of quantum field theory, not to actual particles that exist as discrete objects popping in and out of space. The Feynman diagrams that depict vacuum fluctuations as loops of particles appearing and annihilating are a mathematical bookkeeping device. What is physically real is the fluctuation of quantum fields, the non-zero value of their ground state energy, and the measurable effects that result from that energy. The Casimir force is real, the Lamb shift is real. The virtual particle picture is a useful intuition that should not be taken too literally. The fields themselves and their ground state activity are what the measurements confirm. A third line of evidence comes from astrophysics at a scale incomparably larger than a laboratory gap between metal plates. In 1974, Stephen Hawking at Cambridge combined quantum field theory with the curved spacetime of general relativity and derived a prediction. Near the event horizon of a black hole, the extreme curvature of spacetime causes the quantum vacuum to behave differently on the two sides of the horizon. The result, in simplified terms, is that field modes that would normally be paired across the horizon become separated. One mode falls inward, the corresponding outgoing mode escapes. To a distant observer, the escaping modes appear as a thermal flux of radiation, now called Hawking radiation, with a characteristic temperature inversely proportional to the black hole's mass. A black hole with the mass of the Sun would radiate at approximately 60 nanokelvin, 60 billionths of a Kelvin, far too cold to detect against the cosmic microwave background. Hawking radiation has not been directly observed for astrophysical black holes. It remains a theoretical prediction, although analog experiments using flowing fluids and optical systems have produced laboratory systems where the mathematical analog of Hawking radiation has been observed and the thermal spectrum confirmed. The mechanism is the vacuum. The vacuum fluctuates at the horizon. The curvature of spacetime separates fluctuations that are normally paired. The result is the slow evaporation of the most gravitationally extreme objects in the universe. Now hold these three lines of evidence together, The Casimir force at micrometer scales in a Dutch physicist's calculation, confirmed in a Washington laboratory, the Lamb shift at atomic scales measured with Nobel Prize precision at Columbia, and the predicted evaporation of black holes through horizon-separated vacuum fluctuations. Three different physical regimes, three different measurement techniques, one underlying cause. The vacuum carries energy, the vacuum fluctuates, the vacuum acts. It is not X, not passive empty space, not a blank coordinate system through which matter moves. It is Z, the lowest energy state of every quantum field in existence, irreducibly active, structurally forbidden from stillness. Here is where the honest accounting of evidence becomes important. The Casimir effect is strongly evidenced. Multiple independent measurements since Lamoureux's 1997 experiment have confirmed it to better than 1% in some configurations. The Lamb shift is strongly evidenced. It matches quantum electrodynamic predictions to parts per billion and has been reproduced in every precision hydrogen spectroscopy experiment for 70 years. Hawking radiation is theoretically robust, derived from well-tested components of both quantum field theory and general relativity, but it is physically unconfirmed for real black holes. The analog experiments are consistent with the prediction, but do not constitute direct confirmation of the gravitational mechanism. That distinction matters. Two of the three pillars are measured fact. The third is the most well-motivated, unconfirmed prediction in theoretical physics. There remains a fourth mechanism, and it operates not at the scale of metal plates or hydrogen atoms or black holes, but at the scale of the observable universe itself. Dark energy, the name physicists give to whatever is driving the accelerating expansion of the cosmos, has an energy density that can be inferred from measurements of that expansion. The most precise value comes from the Planck satellite collaboration, which reported a dark energy density of approximately 5.96 times 10 to the negative 10 joules per cubic meter. That is the measurement: quiet, small, real. Now perform the natural calculation. Take the zero-point energy contributions of all quantum field modes up to the energy scale where quantum field theory is expected to remain valid, the Planck scale at approximately 10 to the 19th giga-electron volts, sum the contributions, and convert to energy per cubic meter. The result is approximately 10 to the power of 113 joules per cubic meter. The measured value is approximately 10 to the negative 10 joules per cubic meter. The discrepancy is 10 to the 123rd power. Written as a ratio, the naive theoretical prediction exceeds the observed value by 1 followed by 123 zeros. This is not a rounding error. This is not a unit conversion mistake. This is the cosmological constant problem, and it is the largest quantitative discrepancy between a theoretical prediction and a measurement in the recorded history of science. Physicists have known about it since the 1960s and 1970s, when quantum field theory and cosmology were first carefully compared. No solution exists. Several approaches have been proposed. Supersymmetry, a theoretical framework that pairs every boson with a fermion, predicts that the zero-point energies of bosonic and fermionic fields cancel in pairs, potentially reducing the discrepancy. But supersymmetry, if it exists, is broken at some energy scale, meaning the cancellation is imperfect, and no supersymmetric partner particles have been detected at the Large Hadron Collider up to the energies so far explored. Anthropic arguments from string theory's landscape of possible vacuum states suggest that the small observed value might be a selection effect, that observers can only exist in universes where the vacuum energy is small enough for galaxies to form. But this is a philosophical argument, not a calculation. Some physicists argue that a future theory of quantum gravity will reveal a mechanism that sets the vacuum energy precisely to the observed value. None of these proposals has moved from speculation to confirmation. The cosmological constant problem sits at the intersection of quantum field theory and general relativity, the two most successful physical theories ever constructed, each confirmed in its own domain to extraordinary precision, and their junction produces the most embarrassing number in physics. The vacuum is real, the vacuum is active, and we cannot calculate its energy correctly by a factor of 10 to the 123rd. Both things are simultaneously true. The pharmaceutical industry spends billions developing compounds that modulate the electromagnetic interactions between molecules. Every drug that binds a receptor, every anesthetic that quiets a nerve, every antibiotic that disrupts a bacterial membrane operates through the same electromagnetic force that mediates the Casimir effect. The difference is that the Casimir effect requires no molecule, no bond, no contact. The vacuum itself, in the gap between two uncharged plates, exerts a force of the same fundamental origin as the forces holding every pharmaceutical compound to its target protein. The vacuum is doing for free, in empty space, what the entire global pharmaceutical industry exists to engineer at molecular scale. Return now to your palms on the surface. The solidity you felt, that resistance, is the Pauli exclusion principle, preventing the electron clouds of surface atoms from overlapping with the electron clouds of your skin, a quantum mechanical rule forbidding identical fermions from occupying the same state. But those electron clouds are themselves embedded in and constantly interacting with the fluctuating vacuum. The electrons in the atoms of that surface are experiencing their own Lamb shifts. The electromagnetic field permeating the gap between your skin and the surface at the last moment before contact is the same vacuum carrying Casimir pressure between Lamoureux's metal plates. The vacuum was participating in the resistance you felt. Vacuum fluctuations are not confined to laboratory apparatus. They operate at every point in space at every moment. In the ground state of every atom in every material object, the electron is being nudged by virtual photon modes from the electromagnetic vacuum, its energy levels shifted by amounts that precision spectroscopy can resolve. The vacuum is inside every object. The vacuum is between every pair of adjacent atoms. The vacuum is the medium in which all of chemistry, all of biology, all of physical structure exists. It is not nothing. It has never been nothing. The uncertainty principle prohibits it from being nothing. What you feel when you press your palms against a surface and push is a structure of quantum fields that cannot be made to stand still, organized into matter by rules that exploit the very instability the vacuum cannot escape. Press again. The vacuum is still there, still humming. The ground state never rests.